The U.S. Navy High Point, PCH-1, is operated as an advanced development vessel under the direction of Hydrofoil Special Trials Unit of the Naval Ship Research and Development Center out of Puget Sound Naval Shipyard, Bremerton, Washington. The Boeing Company built High Point in 1962 and now provides program technical support. The High Point has been operated and maintained by a United States Navy crew since 1963. The all-aluminum hull is 116 feet long and displaces 117 tons. The submerged hydrofoil system employs a canard configuration with 70% of the foil area aft. The subcavitating foils are provided with trailing edge flaps that are automatically controlled during foil-borne flight. Rough water trials are conducted from a remote site near the Pacific Ocean. Foil-borne propulsion is provided by 2 pairs of pusher tractor propellers mounted on the aft foil nacelles. Power to the propellers is delivered through right-angle gearboxes driven by 2 3,100 horsepower Proteus gas turbines. With the foils retracted, the craft can navigate the shallower inland water ports, such as Nia Bay, Washington, a convenient remote base site for rough water trials. High Point maneuvers hull-borne with a diesel-powered outdrive. The Pacific Ocean is only a few minutes from this base of operation. The sea surface characteristics associated with sea state numbers are measured while transiting to the desired area. Engineering data acquired during rough water trials are recorded on magnetic tape for future processing and analysis. Critical measurements are displayed instantaneously so that an engineer can monitor speed, wave heights, craft motions of pitch, roll, yaw rate, vertical acceleration, and control surface motions of flaps and rudder. High Point negotiates the ocean waves with the ease of a craft at least 10 times her size at speeds of 40 knots. As the sea builds, some additional power is used to maintain desired foil-borne speed. In a sea state 5, this power differential is approximately 15% at a speed of 36 knots. To maintain acceptable craft performance with respect to increasing sea conditions, it is necessary to reduce craft speed. A 100 high-performance vehicles. Hence G average acceleration as compared to accelerations experienced by other types of craft in comparable seas. In addition, those craft had to reduce speed. Trials conducted on the High Point included variations in heading, foil submergence, speed, and sea state. Operating in sea state 5, the high point in the head sea condition produces the highest foil submergence in high sea states, results in hull slamming and forward foil surfacing. Deeper foil depths produce a milder acceptable effect called cresting. Depending on sea conditions, the best foil submergence would consider personnel comfort and optimum performance. Although the vertical accelerations are observed to be less in the bow sea condition, the same characteristic forward foil surfacing and hull slamming is evident at selected acceleration, especially at shallower foil depths. The quartering, following, and beam sea conditions show a marked decrease in vertical acceleration when compared with the bow and head sea conditions. Accelerations experienced at these headings with respect to the seaway are primarily the result of cresting action with little foil surfacing or hull slamming. Landing, takeoff, and turning tests demonstrated that maneuverability was relatively independent of sea state and craft heading. The modern-day submerged hydrofoil craft, such as the United States Navy High Point, is an excellent example of how man and advanced marine technology are conquering the sea around us.